Hello, welcome to a project Sonic Log Synthesis using signal processing techniques. So now this is a very interesting project for all the people from all the domains because in this we'll be discussing things of different domains. Basically, we'll be predicting sonic log, which is widely used in the petroleum industry or the geophysical industry, with the help of wavelet transformation. That is a signal processing technique which is widely used in the machine learning world, which is used to transform the data, that signal data, into another format. Okay, so we'll be merging these two industries with one, and you'll see that okay, what are the results and what are the things we have obtained. So now, as written during this course of the project, we'll learn about using wavelet transformation, which is one of the signal processing technique, as a feature engineering method, and use it to predict sonic log, which is one of the applications of machine learning in petrophysics industry. So now the moving forward, what is a sonic log? I have turned, we'll be predicting sonic log, but what is a sonic log? So as written, the sonic log is a porosity log that measures interval transit time of compressional sound wave traveling through 1 foot of formation. So now if you guys are from a geophysical background or a petroleum background, you might have heard about it. But for the people who are don't, let me tell you that sonic log is basically one of the log which measures the porosity of a formation. What is a formation? Formation is a chunk of piece of earth. Basically, I dig into the earth, and the kind of the part which I am researching on, that is my formation. Okay, that is my formation. Now I have to find out what is the porosity. Porosity is basically the pore spaces present in between those rock particles, which means that okay, this if the highly porous rock is there, that means it can accumulate more number of things in it, more number of water, more number of crude oil, or any of the things of that sort. Okay, so this is porosity, and the thing which measures it is called as sonic log. And how does it work? It basically sends signals, it basically sends sound signals, which comes back and reflects back, and on the basis of the interval transit time, we measure that compressional sound wave. Now it is on of two forms, one is the compressional and another one is the shear. We'll be predicting two different things in this, DTC and DTS. Now, sonic log is widely used in the geophysics industry, and its synthesis using machine learning techniques will help the people in understanding the formation in a more effective way and in a more economical way. So now what the thing is, in producing this sonic log, there is a huge economical cost involved because the instruments which are used are very vast. Now, if we are able to do this, if we are able to synthesize this log with the help of machine learning, with the help of very good accuracy, see how much economical cost we are saving, right? So this is a very important practice which is done in the field of geophysical or petroleum engineering with the help of machine learning. So I think it is a pretty interesting project to do, and it will surely look good in your resumes and in your project list. So now moving on, what is wavelet transformation? I have talked about, we'll be predicting it, but earlier I said that we'll be using signal processing techniques. So wavelet transformation is a kind of signal processing technique which we'll be using as a feature engineering technique. That means we'll be applying this transformation into our features to see and to obtain or to increase our accuracy. So now what is wavelet transformation? It basically transforms our data from time domain to frequency domain. It basically breaks down our data. What it does, it basically breaks down our data. So now what are wavelets? These are the few terms which you have to be acquainted with. Wavelets. Now what is wavelet? Wavelet is a single piece of signal. That means there's a big signal and slice it up, and I'm taking it in a smaller domain. That means that is a wavelet. And what is a wavelet series? In mathematics, a wavelet series is a representation of square integrable functions by a certain orthonormal series generated by a wavelet. So now I know that this might seem a little bit of more at the mathematical point of view, but again, you don't have to understand all of it. You just have to be need a clear idea. Okay, what is wavelet transformation? What it is doing? Basically, it is transforming a signal, or it is breaking down a signal into more simpler ways, which will help us in predicting our final output. That is the main crux of it. If you want to go deep down, you can surely search for it, you can study about it, but that is another topic of discussion. There are two types of transformation: continuous wavelet transform, discrete wavelet transform. Again, it is not that relevant for a project. Only we have to understand what is wavelet transformation and what it will do to our data. There's a little domain knowledge I am giving you behind the project, so that you are not completely numb when you're doing that project and you're just writing the code and not understanding what are the things which are happening around. Okay, so now moving on, what is the problem statement? So now the problem statement is that we are given a data set which contains different features. That means there are different logs which, with the help of which we'll be predicting our sonic log. There are different logs which I'll be explaining you in the next section. What are these logs and what are these used for and how they will help in predicting. Now we'll just use different machine learning techniques to predict that log data. We'll use different regression models, that is a regression technique. Then we'll apply the wavelet transformation as a feature engineering technique. We'll try to increase the accuracy based on that. Okay, now we'll predict that with the help of transform data, and we'll observe the results. Okay, what is the accuracy which is increased. So by this time you might have a overall idea of what we'll be doing in this project, and as we'll move forward it will get clear. So the timeline is that first we'll be using them data analysis techniques, some feature engineering techniques, the basic data pre-processing techniques, right? Then we'll build our model, then we'll perform the transformation, then we'll again build our model. Okay, this is the whole timeline of the project which will follow. So this will be a pretty interesting project, and I'll see you in the next section in the notebook exercise. Hello all, welcome to the notebook section of this project. In this section, we'll be seeing how we can build the machine learning models, and we'll be performing different operations. So now, as discussed in the introduction part, I have told you what we'll be doing in this project, what wavelet transformation is and what is a sonic log. So now, as written, the project name is Feature Engineering using signal processing to predict DTC and DTS values. Again, DTC and DTS values are the sonic log outputs, that is the compressional and shear wave velocities. In this project, we aim to find out the effect of wavelet transformation, a signal processing technique, on DTC and DTS velocities prediction. As discussed earlier, we'll be using it as a feature engineering technique to enhance our accuracy. Our timeline I've already discussed. First, we'll be using the prediction using normal log data, then we'll perform wavelet transformation, then again we'll see to obtain the results. So now this is a regression technique. As you all know, it is a regression technique. This will be include following steps: importing data, data exploration and preparation, model development, model prediction and evaluation. Okay, so now what also I have taken this data from a synthetic sonic log curves generation contest. Okay, this was a contest which was held in the machine learning domain in the field of petroleum engineering. So this the data is taken from there. I will be providing you the data, don't worry, and I'll explaining you all the details what it is present inside the data. So now this is the description, which means that what are the things as a independent variable which are present inside the data. So these are the different logs, and you don't have to go deep down to what these logs are, because similarly as of any of the machine learning technique in any other domain, you have features, right? So similarly in this, these are your independent variables like the features. So one is the caliper log. This basically measures the whole of a hole, or basically the diameter of a hole in which we are measuring in a formation. Another one is the neutron log, gamma ray log, deep resistivity, medium resistivity, and one is photoelectric factor, density of that particular log, particular formation, and DTC and DTS values are our predictable variables. So now again, if you are from a petroleum engineering or a geological background, you must have known these things. But if you are not, no worry, these are just your features, and you have to perform feature engineering techniques. Okay, you have to build a model for these. So now the very first thing is we have to import libraries and a data set. So the basic libraries are pandas, numpy, cpon, matplotlib for visualization and processing techniques. I've imported train test split to split the data, and for accuracy metrics, mean squared error and r square. And the model which I'll be using is XGBoost. I'll be telling you more about it. Also, I'm using Jupyter Notebook in here. If you are not familiar with Jupyter Notebook, you can have a look what Jupyter Notebook is. It is an IDE similar to many other IDEs which are present. It is basically used for machine learning and using data science projects. Or if you are not familiar with it, you can also use Google Colab, because this requires a little bit processing power from your computer as it runs in a local machine. If your computer is not that powerful enough, so you can use Google Colab. It uses a Google server which provides the GPU and CPU power. So just type Google Colab, look it up, and you will find out, and you can do the same thing in there is no difference, kind of difference in that. So but I'll say Jupyter is a more eco-friendly way, or a more user-friendly ID, where here it will be things are more good or easier, or it is based just basically depends on the preference. If you like Jupyter, you can use Jupyter, or you can either use Colab. It is same, it is the same. So now we have imported the libraries. Then now first what we'll do, we'll import the data. We have trained data basically to train our model, and we have test data to test our model. So we'll just import it, and then let us see how big our data is. As you can see, the train data is around 30,000 rows are there in train data, and in test data there are around 11,000 rows. So now just have a look at the train data statistically. This is the mean, like the mean of all the features. The mean is -8, and all of these things. Maximum value is 21, and all. The similar done is for test data. So now first let us have a look at our data, how our data looks like. Okay, so now if I want to look at my train data, so this is my train data, as you can see. So now you will be showing this -999 values. Okay, what are these are basically the null values. What happens in the log machine, if any value is not recorded, it is termed as -999. That basically means null values. We'll just replace it with it, as I have written that I've imported a column data frame in which I've copied all the data of train DF. Then I'm saying that okay, replace this 999 with nan values. Okay, basically everything which wherever it is present -999, replace it with nan. Okay, so now we have a look at our data, how our data looks like. I've explained you these variables. These are just the independent variables. All these and these two are our dependent variables. So now we'll be proceeding with some data processing techniques or data analysis techniques in our next section. So I'll see you in the next video. Hello all, welcome to the next section of our project, that is the data analysis section. So now in the previous section we have learned about what wavelet transformation is, have a brief introduction about the project, and then we have imported our libraries and understood our data, what our data is statistically, and we have seen our data also. This is our data set actually. We have seen that there are around 30,000 rows in our train data, and around 11,000 rows in our test data. So now what we'll be doing, we'll be doing some data analysis techniques to visualize our data, to understand the data better. Also, I've told you that we have replaced all the values which were -999 with nan values, because they are basically the nan values. So this is our data. Now moving on forward, I'll be plotting a histogram plot. So these are very basic Python commands. If you write df.hist, so it will provide you a histogram plot, basically distribution of the data. So as you can see, this is the distribution of your data. First is the caliper log, in which the values are there, and then it is neutron porosity log, in which, as you can see, the most of the values are around zero, and some of the values might be some outlier only, because that's why it is showing this much scale, huge scale. We'll remove these outliers also. Then this is the gamma ray log, another feature. Similarly, all of these, and these are dependent variables, the DTC and DTS. As you can see, DTC and DTS are quite normally distributed in this range, and in this range also. So now what will do, I'll be using another function, that is df.plot. So this is the basically same. This is plotting a histogram plot, this is plotting a line plot in a horizontal way. So it is actually the same. It is in the form of histogram, it is in the form of line plot, which ranges the values. As you can see how your data is lying, the caliper log, as you can see, it is going up and down, and it is basically the same. Okay, it is almost the same. These, as you can see, these values are same. The one spikes are mostly the outliers. Okay, because some of time it can happen it the machine can read the our wrong reading. Okay, these are termed as outliers. So now what we'll be doing, and also we don't want any of the negative values. Okay, so because these values can't be negative, any of the values is negative, that means it is a no value, null value. So what I did is I'm using all the negative values and nan values. Okay, what I see, what I have written, df zdeen, or because in this negative values were present. So what I have done, okay, if any of these negative values are present, termed this at NaN values. How I did this? I did this using this plot. Okay, I saw that okay, some of the values are negative, so I should put them in NaN section. Okay, so now what we'll be doing also, we'll first create a box plot. We'll first create a box plot to see how what are the outliers. I hope you are familiar with the box plot. What box plot does is it basically plot all your data in a statistical manner. Okay, it will give you the 75th percentile of the data, mean, median, and the 25th percentile, and the dots which you are seeing are the outliers. So now by this process I know, okay, what are the outliers for my data. I have done a simple command. It is present inside sns.boxplot, that is the Seaborn library. You will just write this and the box plot will be there. Okay, I am plotting a box plot. So now see, as you can see, there are many number of outliers present here. Okay, these are the outliers because it is not possible the maximum of the values are lying in this domain and few values are lying around this. So definitely this is an outlier. This is basically a form of human error or entry error or kind of machine error. So what we'll be doing, we'll be removing these values. Okay, I've written a simple code up here which I'm saying that okay, if there is the gamma ray log. Okay, as you can see in the gamma ray log, most of the values which are present here, okay, these are all outliers. Okay, it is not possible if most of the values are having this value and only these are the values which are having this much high value. So what I did, okay, take these only those values which are having the value greater than 250, term that as NaN values. Okay, term that as NaN values. This is the 250 mark and rest of all are NaN values. Okay, the similarly I have done for all the logs, CNC, HRD, HDM. Okay, CNC, HRD, HDM, the same thing I have done here. Okay, and then what the one thing I have done is this is HRM and HRD log. Okay guys, for this you need to have some domain knowledge. I have some domain knowledge and I know that this log, this log is always interpreted in a logarithmic scale. Okay, right now this log is not present in a logarithmic scale. So what I did, I transformed this log in a logarithmic scale. What I did, I applied a log transformation. It converted all these values in a logarithmic values. Okay, that is why how it is conducted. Okay, so now when I'll see, I have removed the outliers, I've transformed this data into a log data. So now if I'll see my box plot, it should be somewhat different. Okay, so now let's see how beautiful it has become. Okay, many of the outliers I have left some of these outliers which are very near to the highest percentile value because that can be possible. Okay, but a case which is far away from our highest value, how is that possible? Okay, that is why that is the case. So as you can see, HRD, HRM, and we'll this CNC value also in the later case. Okay, so now this is the main thing. HRD values remove, HRM values also transform after logarithmic scale. So now what we'll do, we'll just find a correlation. We'll find a correlation for that. Okay, which will predict, which will say that how our values are correlated, right? How our values are correlated to each other. So for that, I'll just use a score called PPS. Okay, I use a score called PPS. What is a PPS? The PPS is a asymmetric data type agnostic score that can detect linear or non-linear relationships between two columns. The score ranges between 0 to 1. That is the same as a correlation matrix. What a correlation matrix is? Correlation matrix tells you the correlation between two features, right? How one feature is related to another. Okay, the same thing it does with the PPS. It is used as an alternative to a correlation matrix because it can tell me the more the linear and the non-linear relationships both. So it works better. So as you can see, this is my PPS matrix in which the value which are here above than point 0, point 2, point 4, that means these values are highly correlated. That means they, as you can see for my DTS and DTC values, these are my predictable values, the dependent values. So as you can see, the ZDN is quite related to that, and when you'll find out like all of these values, how are these correlated to it. So now this is the score, this is basically the PPS score of it. Okay, if you want, you can also plot a correlation matrix. It is also the same. Okay, df.core. Now, if you want, I can plot it for you. SNS dot, when if you'll type sns dot heat map, and if you'll pass it df dot correlation, and if you'll see n naught is equals to true, so you will find out, okay, this is your correlation matrix. It is how easy it is, okay, and that negatively correlated and positively correlated. And not is equals to true, basically to read the data, to display the data on your tiles, okay. So this is your correlation part. This was all about a little data analysis and a little processing part. So now the next thing what we have to do, we have to build our model, okay. We have done all of these things. We don't have to do much for our data. We are not scaling. We have already done the transformation, log transformation, which is required. We have already done all of these things. So the next thing we have to do will prediction. We'll do the predictions using a XGBoost model, which I'll tell you what the model is in the next section. So let's move forward to the next video. All, welcome to the next section of our project, that is the model development phase or the primary model development phase, the first model development phase. So now in the previous section we have had a introduction of our project. We have seen how to import our data, and we have discussed about different IDs like Jupyter Notebook and Google Colab. Then we did some data analysis and processing part on our data. So now the time is to develop our model. So now the very first thing which we'll be doing is we'll just separate our data for different data sets. Okay, as I've said earlier, we have two things to predict. One is the DTC and one is the DTS, the compressional wave velocity and the shear wave velocity. These two combined make up the sonic law. So now what we are doing, we are just creating a kind of different subset, different data set for DTC and DTS. Then we'll just drop the null values. We will just drop the null values because earlier we have turned many of these values as the null values. So for that sake we did that. So now what we have to do, we have to make our independent and dependent variables, right? So this is our independent variables, independent variables for the both, okay, for the both. This is for the both, the and this is our dependent variable, dependent variables, dependent variables. The what we are doing, we are dropping our independent dependent features, okay. We are dropping our final features from that. So this is our independent variables, and we are just taking that and to a dependent variable. Two, we have two, again we have two data sets, one for DTC and another one for DTS. The whole operation will perform two times, okay, because we have two things to predict and we can't predict two things with a single model. We have to create two different models, two different data sets, and we'll be having two different outcomes. So now the next thing which I'll be doing, I am just splitting my data into train and test. DT, okay, sorry, just saying DT, okay, I have not done this. So now, okay, so now train test bit, I hope you're familiar. I've used the test size as 30% and I've used the shuffle word true. Basically, what it'll do, it'll not, what shuffle will do, it'll randomly take the values. Okay, it'll randomly take the values. I've splitted my data into train data and test data similarly for DTC and DTS. So now what I'll be doing, I'll be predicting the model. Okay, I'll be using a XGBoost model. So if you are not familiar with the XGBoost model is an ensemble technique which comes under the boosting technique. So the basic principle of a in boosting ensemble technique is we take one base model, we learn something from it, and then we do the changes in the same model and we proceed further till our changes are completely done. Okay, so XGBoost is stands for extreme gradient boosting model, XGB, that means XGB model, extreme gradient boosting model. So if you want to go into deep maths intuition, you can have a look at it in the internet, you will find out. But in order to see how this works, the main thing is there. So now I'm using these hyperparameters. I obtained this using a grid search model because that is not necessary basically, because in this for the same in this particular project our main aim is we are using a feature engineering technique, okay, which we'll be discussing in the next section. So we'll see the main motive is that. So I've just used the basic parameters which I'll be using. That is the maximum depth for the leaf is 2. We have a learning rate of 0.18. Number of estimate is 145. So if you want to look up what these parameters mean, you can again have a look at the documentation of the XGBoost and have a great look at it. It is pretty good actually. So now I've defined my model. Then I'll say I'm just fitting my model. Okay, what I'm saying is this is for DTC, right? But now, as I have already earlier said, that we have to create two different models. So this is for DTC. I'm fitting my model with my train data. I'm just predicting it. I'm just predicting it, and I'm then finding out the accuracy. Okay, RMSE train, for the train accuracy, how my model is performing on the train data, and the same for test data for the RMSE and the R square both. As you can see, my model is performing pretty good with an accurate test data accuracy of 97 and 0.976 for train data. So now as you can see, it is performing equally good in for the both train and test data. That means my model is pretty good actually. If there is no overfitting or there is no underfitting. So now if I want to see what is the feature importance, because this will be playing a major role in the next section. Okay, based on this only we'll do the feature transformation of our data. We will transformation of our data. So now this in this we can see the CNC log is the most important feature in the prediction level. Okay, so this is the feature importance plot. This is present. This is a feature which is present inside the XGB library. You can do this like XGB dot plot importance. Pass the model. Now for the DTS value, the DTS value will do the same thing, completely same thing, the same data set also. And in this we are getting 98 and 99% accuracy. As you can see, our model is performing a very good in that, because this is basically a train test data which I performed in the train test split, right? We have not touched the real test data till. This is only for training and testing our data to find out, okay, some changes can be done or not. So rather in the next thing we'll be using the test data which is earlier. So I will be performing all those operations which we did in a train data, like the replacing minus 999 values with non values, replacing all the outlier values with that, the same thing which we'll be doing, and performing the log transformation. Then we'll be removing the null values. Okay, we'll be removing the null values. And now we'll see that, okay, there are no null values present. And if we'll see what is the test data shape, that is the 11,088 values. Then we'll just use the same model for the DTC model which we have prepared, and for the DTS model we are obtaining two different results, right? We are obtaining two different results. Okay, so this is my test DF. Okay, as you can see, we appended that value in a test DF value. Okay, so this is the whole prediction thing which we have predicted our values correctly. The next thing we have to do is we'll just find out the accuracy. What is our accuracy for this model? Okay, so that we'll be doing in the next section of the video. So let's proceed. Hello all. Welcome to the next section of this project. So now in this section we'll be evaluating our model which we created in the previous section, right? We created the XGB model. So now in this section we'll be seeing how that model performed. So now in the previous thing you might have seen that in that test data there were only 7 columns. Okay. When I'll go here, if you'll see my test data size, there are only 7 columns. Okay, these are only 7 columns, because in my test data there is no DTC and DTS values present. For that I have a different file which was provided by the same competition in which I took the data, that is under the name real test results CSV. In this the real results are there. In this understand guys, this DTC and DTS is my predicted value which I have predicted from my model. Now I have to see the real test values. Okay, how I will evaluate it, that is my validation data. So this is present in another file. What I'm doing, I am reading that under the in under a data from actual DF. Okay, then I'm saying, okay, pred df I'm saying pred df. Okay, this is my pred df data, I'm combining it, and I'm seeing, okay, this is my pred df. Then I'm converting. So now let's understand that this is my pred df, that DTC and DTS values which I have predicted, and this is the value which is the real value. Okay, actual df is the real value, pred df is the predicted value. I'm converting these values into a kind of array. Okay, I'm saying, okay, convert this into a kind of array. Okay, the array, and this now I'm plotting a function. Now understand guys, this is a very simple function, there is not much to it. I'm plotting a function which will display the results in the form of r square and a scatter plot and a line plot. So now what this function says, I'm saying, okay, define a result plot. In that saying y predict and y real. It will take two parameters. Then it will, what it'll do, it will check the sorry, it will check the accuracy of the predicted data and plot the results. The very first thing it is saying, it is okay, find out the combined r square which is obtaining. Find out the combined r square which is obtaining. The next thing which it doing, it is just reading the data. Okay, the DTC real and the DTS real are the first values which are present in my this value. Understand guys, this in this two different list are present. Okay, two different, this is in the form of list, so there are two different values. One is for DTC and one is for DTS. So I'm just reading those values in the first column and the second column. Then I'm taking r square for both of them. It's a very simple code. If you will have a look, you will understand. I'm plotting a subplot. I'm plotting a plot which will be saying, okay, plot these values. I'm giving my x title, I'm giving my y title. The same thing happening for all of these. I'm plotting four plot. I'm two plotting, I'm from line plot, and two are for scatter plot. Then I'll just pass these, I'll call this function and pass the spread in real values. Okay, so now when I'll pass these, okay, I'll just execute it. So now this is the plot. Okay, how beautiful this plot has become. So now the combined r square is 81%, and the for r square for DTC is 0.90 and DTS is 0.7. Now as you can see, our model is not performed that good in predicting the DTS values. So the another plot also is there in which I can predict this line plot. Okay, this is also a very simple plot. The same thing that I am doing, I am plotting a subplot, and I am saying, okay, plot these results and give me the r square for that. Give me the r square for that. I am plotting my title, x label, y label, and for the my another plot. This is a very simple code. If you will have a look at it, you will understand what these things are written. Don't get confused by all of this code. It is a pretty simple code. I'm just asking my r square. I'm just telling, okay, plot these values, and I'm just obtaining these values. Okay, I is equals to 0, and that means I is equals to 0. That means the first value. Okay, in this I is equals to 1, that means the second value. Here the 1 will be there. Okay, that means the second column, second column of that list for the DTS value. So as you can see, this is my RMSE for the, this is for was for r square. This is my RMSE, two parameters I have used for predictions. Okay, so now as you can see, we have obtained the results. The 90% is for the DTC and 71% is DTS. Also, I have used DTS. You can also use PyCaret library, which is a kind of automated machine learning library. We'll be not using that here because that is not much effective, and that is a whole another topic for it. For that, you can see the automated machine learning playlist. In that, you'll find out all of these things, all of these libraries, how we to use these libraries, and all of those sorts. Okay, so now in this section we have done the prediction, we have estimated, okay, the what are the values, and we have obtained that our model is performing good for DTC prediction but not for DTS. So now in the next section, what we'll be doing, we'll be performing a feature engineering technique called wavelet transformation, and then we'll obtain the results and see how good our accuracy has become. So let's proceed. Hello all, welcome to the next section of our project, that is the wavelet transformation technique. How to do the wavelet transformation. So now previously in our back videos, we have done all of the feature engineering data analysis things, and we also predicted our shear and compressional wave velocities with the help of a XGBoost model. So now the next thing what we'll be doing is we'll be transforming our data into by the help of wavelet transformation, right? So now previously I said, when I showed you the feature importance graph, I told you that okay, this will be a very important thing. Because why will it be an important thing, I'll show you now. Because in this, in the DTC prediction, when you see that the CNC log is of the highest importance, and for the DTS prediction, the GR value is of the highest prediction. Okay, so now what we'll be doing is we will be performing a transformation on only one of the feature, and the reason for that is the main reason is when you perform the wavelet transformation, it creates a huge number of features, right? For the one log, what it will do, it will decompose that signal into various levels, and it will create to the wavelet transformation create two different two different coefficients. One is the approx coefficient, and second one is the detailed coefficients. I didn't tell you earlier this, but it creates two different coefficients, and these two coefficients are nothing but the value of the broken down signals, the value of the broken down signals which a transformation signal has created, right? So and there are different levels. It depends on how much level you want to break down your signal to. Suppose I have set my level to 4. That means I'll break my signal to 4 different levels. Okay, I'll break it, then I'll break it again, I'll break it again, I'll break it again. These are like 4 types, and there are 2 different coefficients. So like 4 level of breaking for one coefficient, another 4 level breaking of another coefficient. That means the total number is 8 coefficients. So if you'll imagine, for one feature it is producing about 8 more columns, and the rest of the independent features are there. So it is producing 8 more columns. That means, okay, it will be creating a many number of layers, right? So we tend to perform this transformation on only one feature which have the highest importance. Then we'll see the results. Otherwise, what it will do, if we will perform the transformation in all of the data, what it will do, it will actually create a huge number of features which can lead to curse of dimensionality, or the overfitting of a model, overgeneralization of a model, many of those things. And then you have to do you have to select those features, and you have to do PDA and all of those things. So in here, for the sake of our results, what we are doing, we are just transforming or one feature, the most important feature in a prediction, which we have seen in both of the cases. So now the very first thing which we'll be doing is, okay, this is also one sharp value. This is same as of the feature importance. The sharp value also gives us the important value. As you can see, for the DTS value, the CNC is having the highest model. Okay, in the previous also we saw that CNC is the highest important feature for DTC prediction, right? So this is the same thing here also. It is the same thing. You can just go with the feature engineering part. You don't have to see this for a lot. So now the next thing comes is the wavelet transformation function. Okay, so now I have created a function which, what it will do, it will basically do the wavelet transformation for you. Earlier in the introduction part, I told you that you don't need to mug up the mathematics part. The Python will do it for you. So as I said, that there are two coefficients. One is the approximate coefficient, and another one is the detailed coefficients. We have written two different functions. Basically they are approximately the same, only some of the changes are there for CA and CD for the different coefficients. So now the very first thing it is saying, I have defined a function make dwt vars CA. Well, CA means approximate coefficients, right? So well df, I am taking well df logs levels wavelet, which wavelet I have to use, how many levels, which log will I use, and well df, that means the whole data set. Now the very first thing it is doing, it is doing is creating wavelets. Okay, it is assigning these. Okay, this is the Python library for wavelet which you do. Then I'm saying, okay, I'm finding out my depth. Okay, I'm finding out depth. The wavelet transformation will happen on the basis of the depth of the depth. You don't have to like mug up or understand this fully. This is a very common function, and you can directly run it in your site also to kind of do the transformation. I'm just explaining you the basic of the what are the things involved in this function. So now the very it will do, it will group my data on the basis of depth. Then it will create a new data frame tempdf, in which the depth will be present. So now what will happen, it will say for log in logs, basically the logs which I have performed, but I'll be giving only one log. Okay, so now it will say in levels, also level I have to give I suppose I have given 4 levels. Okay, so it will iterate through 0 1 2 3 4 5 times. Okay, so levels mean that number of times it will decompose my signal. This is a command where pywavelet is a library present in Python which is used to do the transformation. So CACD, this is the wavelet temp data, that means the data wavelet is actually the wavelet which I'll be giving, there are different types of wavelet. There are DB4 wavelet, HAR wavelet. Here I'll be using DB4 wavelet. So now if you'll just study about, if you want to gain more knowledge about it, you can just Google and say that how many wavelets are there. Basically they are just different mathematical functions which will convert the data different types. Okay, you can see apply different wavelets and see what is the result you are gaining it, right? So now what I'm doing, I'm saying that, okay, give me the first value, give me the value of those, and I'm just concatenating my the values with my current data frame. Okay, what I'm doing is I'm doing just taking my I'm just interpolating. Okay, this is kind of a more in the mathematical or the programming kind of way to make this function. I'll make you as simple as possible. What I am doing is I am just interpolating. I am interpolating my wavelet values which are obtained on the basis of my depth, on the basis of my depth. Okay, on the basis of my depth. So now what this thing is happening. So now what, and then what I'm saying, I'm creating a new feature with all those wavelet transformation features columns which we have created on the basis of level. That means that the log plus CA level 1, CA level 2, CA level 3, like that. Okay, now I'm just appending it on my creating a new DF and appending it in here. Okay, so this was a function to create the approximate coefficients, and this is for the detailed coefficients. The only difference is here here the I am taking my CD, that is for the one. Here I am taking my zero value. Okay, here I am taking my first value. Okay, the zero it is for approximate, the one created is for the detailed coefficient. The same thing I have done here. So now what we'll do, we'll just we'll do the transformation data. So now what I'll do, I'll just create a new data frame, in which it is always good to create new data frames rather than performing the operation on the same data set, right? So I'm just creating a new data frame called DF wavelet. From that data frame, I am just dropping all the null values. I'm seeing what is my data frame. After dropping, I have a 20,516 rows of data set. So now what I'm creating, I don't have a depth column. And in order to do the transformation, I have to create a depth column. So what I am doing, I am generating a certain amount of depth values between 500 to 4,000 for my level of formation, depending on the length of this. So around 20,516 values will be created between 500 to 4,000. Then I am just creating a new feature out of it. Okay, I'm just creating a new feature out of it. So now if you'll see your DF wavelet, now if you'll see your DF wavelet, so see, this is the new depth values are also created. So now what I'll do, I'll just import my transformation. I'm just saying import pi wavelet from SkyPy inter PLD to make these functions work. Okay, so now the what I'm doing, I'm just calling that function. I'm just calling that function. I'm passing the parameters like, well, df is my df wavelet, the data set, and the log is only the one log which I'll be using, that is the CNC log. The level I have told you I'll be using 4 levels, and the wavelet which I'll be using is DB4. There's another wavelet called HAR wavelet. You can also check out on doing that one. So I'll just simply execute this, and as you can see, it is done. That function has completed the transformation. Now let's see. Now what I am doing is I am just saying that, okay, give me, I am just adding these values. I am just making them into a list, and I am concatenating that into my particular my data frame. Okay, I am into my previous data frame. I'm saying, okay, for var df in list df var, that is the list of these two columns, and I'm just saying, okay, concatenate these two in my temp df. On my combined, I'm just saying, okay, make a combined df and merge both of them. Okay, merge both of them, and I'm just saying replace all the nan values. And just now finally I'm just saying that, okay, do that combined df termed as training data. I am just storing that in a new data frame called training data. Now if you'll see the shape, there are around 2,55,160 rows. As you can see, the transformation of what our wavelet transformation is done. From 20,000 rows, it has created around 2,05,160 rows. Okay, so this is what the transformation has done in around 18 columns. So this is what we have done. Now if you want to view, okay, what is the transformation, what is the transformation which we have done. So now what I'm this is a simple function. I'm just taking my plot values, the subplots I have created. I'm saying, okay, ex0 dot plot the plot this value and plot all of these things. I'm just writing the I'm just what I'm just giving my labels. Okay, the CNC CD level 1, CD level 2. Now when you see this figure, then you'll see that, okay, in CNC log, the very first thing, this was your log. Okay, a very kind of mixed up. Then when the level 1, it got decomposed to a kind of level. Okay, then in say level 2, it got more decomposed to level 3, then level 4. When you'll see the difference, the CNC log and CNC level 4, as you can see, it is more discrete, it is more well versed. So this is the magic the wavelet transformation does to a signal. So now the same procedure, now the same thing. Now the next, in the next section, what we'll do, we'll try to predict the same thing which we have done with our transform data and see the results. Hello all and welcome to the final section of our project. So now in this section what we'll be doing is we'll be finally predicting our results and seeing the changes which we have done in our prediction results, our accuracy results after the feature engineering technique called wavelet transformation that we have performed in our data. So now the next thing we have to do is we'll be doing the same thing which we did earlier in the model development phase. We'll create two different data frames for a DTC and DTS. Now this time at the data frame is the transform data, the training data which we created in the previous version. So this is our training data. So now the next thing which we'll be doing, we'll be creating our x values and y values. This is our basically the independent independent variables, and this is basically our dependent variables. This is a dependent variable, these are independent variables. We'll do the train test, we'll do the train test. Okay, so now the very simple thing, then the next model we'll be doing, we'll be using the same model that which we use, that's with the same hyperparameters, everything is the same. The only difference created is the transform data, is the data which we have created. Now when you will see, now this is the, for the DTC and DTS, we are currently training our data. So now in the previous section, you saw that it is approximately the same. It was 97, now here is 98, because the model usually performed well in the trained data. Now the thing we have to see how our model will perform in the actual test data, which where the model was performing with an accuracy of around 81%, the overall accuracy, and around 71% for DTS and 90% for DTC. So now the next thing we have to see is how a model performs with this test data. Okay, so now what we'll do, we'll just say our test data, the same test data which we used there. So only the thing is we have to perform the transformation in this data also, because this is the data but we have trained the model in with the transform data, right? So we have to transform this data also. So we'll perform the wavelet transformation for the same in this data. The same thing I have done here, I'm using the same function, I'm using the same code which I have did. Okay, as you can see, these are the number of test data models which we have created. So now what we'll do, I'll just say, okay, I'm creating two different data sets for my DTC and DTS prediction. Then I'll just finally predict my all the columns. I'll just finally predict my all the different DTC and DTS values. The same function I have used, the model DTC and DTS wave. So now the next thing is, as you can see, this is my transform data. Okay, the DTC level, DTS level 1, level 2, level 3, all of these things. Okay, the same thing which was done in my train data, I'm doing the same thing in my testing data. So now what I'm doing, I'm just creating all of these things. I've created my levels. The DTC and DTS values are my predicted values which I have predicted in the earlier also. So now what I'll do, I'll use all of the things same, all of my these things are same. I'm just plotting my residuals. Okay, so now, okay, the next thing what I did is this was done for my DTC wise. Okay, so now the in the previous section we saw that in our both of the DTC and DTS prediction, we have different features which have the highest of the wave, highest of the feature importance. So now for the DTS prediction, we had a caliper log. So in this, we'll be doing the transformation on the caliper log. In the previously, we did the transformation on the CNC log. So this is what, because of the log, the feature importance graph which we saw. Okay, so now same thing I'll be doing, and I'm just plotting this. Okay, this is my caliper log. Okay, thus previously was my CNC log, this is my caliper log. I know this will be a little bit complex to you, but when you'll see the code and when you'll hear my recording, this, when you will see this video twice, you'll understand all of it. You may have some problem in understanding this the very first time you see it, but as soon as you run through the code, as soon as you see, okay, what are the things which are done in the code and what the things I am speaking, it will be much clear to you. That same thing I am doing, I'm just performing. Earlier I did that on my CNC log, now I'm doing that on my caliper log. The only thing difference is there. Okay, the only thing is there that everything is same, everything is same. Okay, so now this is my whole residual plot. So this is my whole plot. As you can see, most of the residual values are running on 0. That means our predicted values are very good. Now I am using the same function which I used in previously. So now when we'll see the difference, the DTC value prediction is around 92. Earlier it was 0.90, right? Now it has increased with 2%, and we have a drastic change in the DTS values. Earlier it was around 0.71. When you'll see the DT that prediction accuracy, earlier it was around 0.71. As you can see, it is around 0.71, it is 0.90. See how drastically our accuracy has increased, and that means our method has worked, right? Our method is worked. So similarly, I'll plot another graph. So as you can see, this is my overall accuracy, my 92 for my DTC and DTS. If I want to see the overall accuracy, the 0.88, earlier it was 0.81. As you can see, the overall 0.7 accuracy, 0.7% accuracy has increased. That is a very drastic change and a very dramatic change in if we are working on a project. Okay, see how effortlessly we have increased our accuracy, and how good the work has done. The wavelet transformation has worked for us, right? So now go through this video and go through the code. You'll understand. I'll be providing all the different data files, all the different CSV files which are required in this. This is the function. Go to the wavelet transformation function, and if you want to go deep down into it, just search wavelet transformation. You'll gain all the access details, all of those things. And okay, this is the whole notebook which will be provided to you. Go through this notebook once. You'll understand, okay, all of the things we have done. It may look complicated, but it is sure as simple if you'll go through it once again, and go through these videos, and I'm sure you'll definitely grasp it at the end of the time. So thank you for this project.